Good evening, everyone. My name is Eric DiMarzio, and I'd like to welcome you back to another Tech Talk in our series sponsored by Remake Labs. Today, we have the pleasure of welcoming Eric Shagrin to give us a brief talk about mixture of experts architecture. So, without further ado, I'd like to pass it on over to you, Eric.
Thanks so much, Eric. And thank you to Remake Labs for sponsoring this tech talk. Today, I want to give a talk called Dividing the Monolith, which is going to be about mixture of experts architecture in sort of modern AI systems. When you think about most major AI systems that we use today, they have something in common, and that is that they are what is called monolithic. Now, by monolithic, what I mean is that there's a single large model where all of the parameters are involved in processing every single input. So all of the weights are used in all examples. Now, what this means is the cost of of monolithic architecture is actually quite large. So the inference cost, as models become larger, the inference cost increases linearly, whereas the training cost actually increases quadratically. So in monolithic systems, there's a quadratic blowup to training. Now, this matters hugely because scaling laws have become like a very important topic in AI, where the idea is that like as models become larger, the loss decreases, which the effect of that effectively is that they become smarter. This also has continued, just so you know. So in December of last year, there was this very important breakthrough that happened where this is an example of what was called the ARC test. So on the top, you can see these are a series of in this test, a system needs to determine which you need to complete the pattern. What's interesting about this is that humans find this trivially easy, but AI systems to date have had a very difficult time doing this, even up until like September of last year. But then, crucially, in December of last year, this test was also crushed. So this is kind of the most recent of a series of benchmarks that has been kind of dealt with. The cost of it was very expensive. That was $3,000 per input. And so you can see this is just kind of the part of the general kind of emerging capabilities coming from these like very large systems, but at a very large cost. And this matters a whole bunch because this, if we kind of like go back a little bit, just to kind of set some context for what I'm going to talk about with regard to mixture of experts, if we project basically from like 2010 up until the present day, there's been approximately a 4x increase in the size of these AI systems every like year upon year. This is like totally like massive. Just quantitatively, at least over a short period of time, is leader of the pack of like major kind of scientific developments that have happened recently. And if you project this into the future, it's honestly just kind of an extraordinary picture of just like the amount of machinery, the amount of just like how large these systems would get theoretically. And this matters a lot just from like an infrastructure perspective, like the cost of running a single training run would be 6 GW by 2030, which is like getting up to single digit points for a nation state. It's like really kind of a crazy situation. And so you get these constraints. This is all like kind of rigorous and interesting economic modeling that's been done, basically just showing like that these are kind of key constraints that would come from these like monolithic systems. And so there has been a kind of increasing need and desire to try to think through different forms of architecture that might be more that are kind of dealing with some of these kind of like key constraints, bringing us to mixture of experts architecture. So what is this? So mixture of experts architecture is sparse. What do I mean by that? An MOE breaks a model down into multiple components or experts and dynamically selects which subset of experts to use for a given input. So, for example, we have in this system, we have what's called a gate, which is connected to a series of kind of disaggregated sort of experts, and then there's an aggregator that comes out of the end of this thing. How does this work? As an example, there's a query which would go to a gate. There are different kinds of gates. Let's go with hard gating. This is a simpler one. And in this context, what would happen is there would be an identification of which expert would be best for dealing with this particular problem. Semantics versus syntax might be is a real research example of an expert that is specialized in that domain. And so there might be a selection for semantics for this particular expert. And so that then goes to the end of the aggregator, and then you get a token, a single token, which is dealt with by that expert. Then a different expert would deal with the next token and the next one and the next one. It just kind of continues until you get this like single aggregated response. This is different, a different form of gating, just FYI. It's called like soft gating. Soft gating is very cool. It basically takes it averages over a series of experts. And so you actually get much more of there's a very interesting kind of like, there's a route handling that's being handled here in a major way. And so in this case, the aggregator is going to have like a much more important role where it actually averages over a number of different experts that are being dealt with, which then produces this response. So here's why this matters. Like, here's why this is really crucial. In a mixture of expert system, only a small fraction of the total parameters are active for a single input. It's 1/n. So in this case, it would be like 1/5. It has 1/5 of the cost of the inference cost. And additionally, a expert network handles every single query and every single token of every query. These are huge advantages. If we look at just a kind of a comparison between a number of these different AI systems, the top are all monolithic, the bottom are all MOE. And notice that in the top, the number of parameters, total parameters, to the number of active parameters is identical. So the whole system is involved when it's activated. But in MOE, that's not true. You might notice also that the MOE, the total number of parameters, is just super huge. MOE systems are massive. They are almost an order of magnitude larger than their other competitors. This is not the only reason why DeepSeek is kind of relevant, but it's one of the reasons why DeepSeek was like the first. Is kind of like first major production system that is MOE. Doing just a head-to-head here to see kind of like how monolithic versus MOE compares on other benchmarks. If we look across like reasoning, math, coding ability, and you just look between O3 Mini and DeepSeek. So these are the two kind of like most state-of-the-art systems. Up until yesterday, there was actually a release. 3.7 Sonnet is now leader of the pack, unfortunately. Very cool though. This is just a very dynamic space that I did this slide on Sunday and it is now actually out of date. But if you look at just comparing these, reasoning, math, coding ability are all identical, but cost and efficiency differs dramatically. The cost of MOE is almost an order of magnitude cheaper than monolithic in an ideal case, but it's quite dramatic. So looking back at this graph of costs, the cost of training an expert is still a quadratic, but they're much, much smaller. And with a quadratic, you pay for the cost of it mostly at the end. The larger it gets, that the final X values like matter a whole lot than the beginning ones. So they're much smaller quadratics. And additionally, the inference cost is sublinear because it's 1/n, or even in the case of a soft gate, it's still not nearly as much as like using the entire system. So it's cheaper both in inference and it's cheaper in terms of training. Just to give a kind of thinking about where this is going to go, because it's super like very much at the time. There's this really interesting technical interview with Jeff Dean, he's a chief scientist at Google Research. This is from February of 2025. What he says is that sparse mixture of experts models let different parts of a system focus on different tasks. So for instance, in our Gemini 1.5 Pro model, only the relevant expert is activated when processing a specific token. One might handle math, another one cat images, and so on. This approach can maintain high overall capacity while keeping inference efficient, exactly like we've just discussed. But here's what's interesting. Current mixtures of experts typically rely only on uniform and regularly merging branches. A more organic structure could allow distinct components to develop independently, specializing in South Asian languages or Haskell code or whatever. Teams and companies could then create optimal data and training techniques for their specialty, and then plug in their expert model into this larger system. And this modular strategy, it simplifies software engineering. Instead of a single monolithic training process, multiple teams can work in parallel on different components. Effectively, it's a form of continual learning without having to overhaul the entire system capacity every time. But what's also interesting is this is like kind of controversial. So OpenAI released a report in February of 2025, and they are very much don't agree with this point of view. They are of the position instead that they're really for training like more monolithic systems. So in this report, they basically they tested a trained version of O3 Mini, and what they said is scaling general purpose reinforcement learning rather than relying on domain specific techniques offers a robust path towards state-of-the-art AI in reasoning domains such as in competitive programming. So they're really of the position, it seems, that monolithic systems are actually the way to go. So there's a really kind of interesting division going on. Just to use a total kind of poetic metaphor thing, these truly monolithic systems, this is their MOE and monolithic systems are not actually really in opposition to each other. They are to some extent in some kind of dynamic with each other, where the truly monolithic kind of act as like the most cutting edge thing that are kind of able to have this like general emergent ability. And then you get these smaller systems that are kind of like developing behind that allow for software engineers to build like knowledge systems that kind of make use of these distilled models, mixture of expert models, and all of these other kind of like more knowledge systems that are developing. Now, I just want to say, if this doesn't seem relevant, if this seems like some wild cutting edge ML stuff that like software engineers are like maybe wouldn't be relevant to know, like think about RAG. RAG was a insane ML, very complicated thing 2 years ago. Like no one knew how to do it. And now it is just totally a standard thing that is expected that an entry-level software engineer has an idea about. And the same, I think, probably will be true of developing these other kinds of systems. Finally, these are my references. Um, but the really detailed research is actually it's on my website, ericshagrin.notion.site. This is actually a much better way of dealing with this information. I encourage you to go there and look for this icon, which is on dividing the monolith. That's it. Thanks so much.
Thank you so much for that informative talk, and thank you everyone for coming out tonight. We'll see you at the next one.